To understand alternating current, it helps to look at direct current. DC flows in only one direction, and so in a simple battery circuit like this, the amperage will stay positive. So if you graph a DC voltage or a DC current, it would just look like this. Alternating current, on the other hand, changes direction periodically, and so if you spin an AC generator, you can watch the ammeter change. Typical AC sources like generators create sine waves, and so if you graph their voltage, they would look like this. Unlike DC sources like batteries or commutated generators, AC is generated by rotating a magnetic field with respect to conductors. And so if you turn a magnet like this, with respect to copper coils, an AC voltage is induced in the conductors. This can be done with either electromagnets like this or permanent magnets. But the reason that electromagnets are used in most cases is because if you change the current flowing into the electromagnet, you can change the strength of the field. And what that does is it allows you to change the amount of power coming out of the generator without changing the speed of the generator. This is just a typical car alternator I've got here, but it happens to be a perfect example of AC generators you might find at power stations, and that's because on the inside it's got three-phase stator windings here, and an electromagnet for a rotor, and that means there are no permanent magnets on the inside. But having no permanent magnets inside means that if you just turn the AC generator, nothing happens. What little movement you do see in the ammeter is just from residual magnetism in the rotor. But to generate a usable amount of power, you have to apply a small direct current to the rotor. What that does is it magnetizes it, and so now, if you turn it, an AC voltage is induced. You might think generating electricity this way is inefficient, and to a certain extent you'd be right, because it takes electricity to make electricity. However, keep in mind that as you increase the speed of the generator, the output power increases, while the field current stays the same. And so if you spin the generator to a certain speed, say a few thousand RPMs, you can get over 100 times the amount of power out that you put in. But what I've shown you so far is just a single phase of alternating current. And it looks like this, it's just the sine wave from before. But because this is a three-phase stator, what is present is actually three sine waves. And so there will be three different alternating currents inside induced every time you turn the rotor. But the reason three-phase is used more often than single-phase is because if you just look at a single-phase signal, it's just one sine wave, and what that means is that every time there's a dip here, or the wave crosses the 0 point, there's a node, and at a node, zero power is being generated. Three-phase, however, there's always at least one sine wave on a positive track up or down, no matter where the rotor is in its turn. And so that means the total output power is always going to be fairly high, and the output waveform of power will look something like this, as opposed to single phase, which would look like this. So basically the output power waveform of single phase is gross and bumpy like this, and basically you don't want that. If you're dealing with bulk power transmission, you want three phase because it's more efficient, smoother, and it's just better. But let's get back to the power being generated. Right now the ammeter is hooked up between phases B and C, and the voltmeter is hooked up between phases C and A. And of course these aren't to measure voltage or amperage, they're just to show you the different waveforms. And so if I turn the generator, you'll see that while both needles rise and fall, they do so out of time from one another. And what that means is that they're out of phase. And if I had a third meter that was more appropriately scaled, then you'd be able to see that all three phases would do so. Now there are two different ways you can wire the stator in a three-phase generator. You can either use the Y configuration, also called the star configuration, or the delta configuration. The star configuration is the most common because it's easy to ground the system. In delta, of course, all you have are the three phases, and so ground would need to be one of the phase conductors. And for obvious reasons, it's not very practical to ground an actual conductor. And so that's why we use star. And these configurations have these symbols. Y just literally looks like a Y, and the delta configuration looks like a triangle. Taking another look at the star configuration, you can see that there are three different voltages present with a stator wound in series like this. there are three phases and a neutral. There's the voltage between the neutral and any phase, and also the voltages between phases. And if the line voltage is x, the voltage between lines or between phases is x times the square root of 3. And this is also called the system voltage. And so if each coil is generating 120 volts, then the full system voltage will be 208 volts, because 120 times the square root of 3 is about 208. And 208 would be the voltage between phases. To understand why this relationship is the square root of 3, it helps to look at a circle. So let's pretend that this circle is a generator, and each of these radius lengths is a phase of the generator. And so the line voltage here would be this distance, we can call it x, and the line-to-line voltage will be this distance. But what happens when you do this with each of the lengths equally 120 degrees apart is you create what's called a special triangle. And in a special triangle, you can always use a rule to figure out what the side lengths are. And this particular triangle is called a 30-30-120 triangle because of the internal angles. And in a 30-30-120 triangle, if the smaller legs are each x distance, then the bigger leg will always be x times the square root of 3. And so taking this back to electrical systems, if you've got a 120 volt system, that's 3-phase, multiplied by the square root of 3 will give you the system voltage of 208. This is always expressed as system voltage first, and then the phase voltage second, like this. Likewise, in a 480 volt system, to find the line voltage, just divide 480 by the square root of 3, and you get about 277, and so you'd write that like this. Thank you guys so much for watching. If you liked this video or learned something new, please leave a thumbs up. Or if you've got a question and you want something explained, leave a comment and I'll see what I can do. And lastly, thanks for stopping in.